Now, as I mentioned earlier, we cut through that stress element in order to determine those equations. Now, I didn't do the full derivation. You can look that up in your textbook. However, you could have just rotated your stress element and figured everything out. Like all you had to do is rotate it and work out the forces again, and you'll be able to solve for these new tangential and normal stresses, as well as the shear stresses. So one thing you might begin to wonder is, if I'm rotating this element, could I find a point where the shear stress or strain is a maximum, or where the shear stress or strain disappears entirely? And there actually is an orientation. There's always an orientation where the shear stress, and I'm saying shear stress and strain, is 0. Okay? And the normal stresses for this orientation are referred to as the principal stresses or principal strains, depending which one you're looking at. So let's look at this and see if we can solve for it. So to derive this, what you do is you take the derivative of our equations we had earlier. So if I were to jump back, actually I'm going to jump back a little bit more. Boom, 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 boom. These equations right here, if I take the derivative of these with respect to theta, I can look and find where the stress is a maximum or where the shear stress is a minimum. And that's important. That's how we're actually going to calculate this. Okay, jumping forward again. There we go. So if I take the derivative of those normal and shear stresses, or normal and shear strains, with respect to the angle, then I can solve for that minimum maximum. And I'll get these equations. And the amazing thing is they are so incredibly similar. Like this one right here is literally identical, except for the fact that we have strain on one side and stress on the other. Now this angle right here is the principal angle. It's the angle we have to rotate our element to get to our principal axes. You're like, well, what am I rotating from? Well, you're rotating from wherever you started. Okay, from wherever you started, you can rotate to get to your principal axes. And that's really visualized well when you have Mohr's circle later. The second one right here, you can see that it's almost identical, but once again, we have that whole shear strain is divided by 2. Otherwise, we're just replacing stress with strain. And down here at the bottom, once again, the only difference is that the shear strain is divided by 2. Now, I did it in this order on purpose because, this is very, very helpful. What you see is that the principal stresses are equal to your average stress, so whatever your state was before, plus or minus the maximum shear stress or maximum shear strain. The reason for this is that all of your stress states, they fall on this nice little circle called Mohr's circle. Same thing with strains. And the center of Mohr's circle, which isn't always right where the axes are, is your average stress, your average normal stress. And the radius of Mohr's circle is actually your max shear stress or max shear strain. So that is important. That is helpful. Eventually, it's going to be an absolutely amazing visualization tool. So once again, some arrows, which if I hadn't drawn so much, you'll be able to see, pointing out those differences because they're very, very similar, but they're not identical. Okay, so we'll stop here, and then next time we're going to jump into Mohr's circle for plane stress. And as a note, well, I'll say that next time, but Mohr's circle for plane stress. So have a good day. Thank you for listening, and I'll see you all later. Bye-bye.